Inside a single human cell, billions of molecular machines are constantly at work. It acts as a bustling metropolis of proteins, DNA, and RNA, all moving in continuous, intricate choreography. In 2020, an AI model called AlphaFold 2 mapped the three-dimensional shapes of hundreds of millions of individual proteins, a feat that provided researchers with a structural library for nearly every known protein sequence. But having the shape of an isolated protein is like holding a single, beautifully crafted gear from a Swiss watch. It just sits alone on a table. You know its exact dimensions, but that doesn't explain how the entire watch ticks. More importantly, it doesn't tell you how to repair the mechanism if it stops working. No piece of biology works in isolation. To truly understand how life operates and the diseases that disrupt it, we have to see how all these distinct molecular gears interlock and turn together. For a protein to actually perform its function, it has to physically connect with other structures, like DNA, RNA, and small molecules called ligands. Historically, figuring out exactly how just one of these connections snaps together requires years of laboratory experiments. It often costs hundreds of thousands of dollars and takes the length of an entire PhD program to map a single interaction. Multiply that effort by the millions of unique molecular combinations happening inside us right now. The sheer mathematical scale makes it impossible to map every interaction manually. Until we can visualize these complex interactions rapidly, discovering a new drug remains a slow process of physical trial and error. AlphaFold 3 was built to unify these disparate pieces. Developed by Google DeepMind and Isomorphic Labs, this model predicts the joint three-dimensional structures of all life's molecules fitting together. It starts with an improved version of the EvoFormer module, a deep learning architecture that takes a list of input molecules and processes their underlying biological data. Then it hands that data off to a diffusion network, the same type of AI technology used in modern image generators. The assembly begins with a cloud of atoms. Over many distinct steps, the diffusion network refines it step by step, converging on a precise, interlocking molecular structure. What used to take years of experimental biology can now be computed in seconds, turning biological noise into a high-definition, actionable blueprint. This chart shows how AlphaFold 3 performs against the best traditional methods on the PoseBusters benchmark. For predicting protein interactions, it represents at least a 50% improvement. And when we look at certain critical categories of molecular interaction, that prediction accuracy actually doubles. This makes it the first artificial intelligence system to surpass physics-based tools for biomolecular structure prediction. While physical experiments remain the necessary final step for verification, these digital models provide a reliable map of molecular reality that was previously out of reach for computation. This level of detail has immediate implications for human health. AlphaFold 3 specifically targets how proteins bind with ligands and antibodies, the primary molecules used in most modern therapeutic drugs. Isomorphic Labs is already putting this into practice. They are collaborating with pharmaceutical companies, using these structural predictions to help design new treatments for patients. Because they can model exactly how an antibody binds to a target protein, researchers can now tackle disease pathways that were previously considered unreachable. Scientists no longer have to guess how a synthetic molecule might attach to a diseased cell. They can see the physical mechanism on a screen before a physical experiment is run. To assist global science, Google DeepMind launched the AlphaFold server, making the majority of the model's capabilities free for non-commercial research. This gives biologists anywhere in the world an accessible way to generate structural predictions. A researcher investigating neglected diseases doesn't need high-level machine learning expertise to test a novel hypothesis. The implications stretch beyond human medicine. Mapping these deep molecular connections provides a new framework for genomics research. In agriculture, understanding how specific enzymes interact with plant cells gives researchers a direct path to developing more resilient crops that can withstand harsher climates. By predicting how these molecular pieces fit together, AlphaFold 3 reduces a primary bottleneck in biological research, helping discovery move at the speed of software.